At the edge of the solar system, a line of frozen worlds is hiding in the dark. They look quiet, but James Webb is reading them like sealed letters right now. One by one, their surfaces are answering a question nobody could settle for decades. And the answer says Pluto is not standing at the end of a simple empty frontier. If that kind of space secret pulls you in, subscribe now. This is where we follow the strangest real science stories all the way back to the evidence. And if you like mysteries that grow bigger when the data gets better, stay with me. For a long time, most people treated Pluto like the lonely last stop of the solar system. It was discovered in 1930 by Clyde Tombaugh at Lowell Observatory, and for years it felt like the final world on the map. Far beyond the giant planets, beyond the warm inner system, Pluto seemed to sit in a cold, silent place with almost nothing around it. That picture was simple, neat, and very wrong. In 1992, astronomers Dave Jewett and Jane Liu found another object beyond Neptune, later named Albion. That changed everything because Pluto was no longer a strange one-off object sitting by itself in the dark. It became the first known member of a huge family now called trans-Neptunian objects, or TNOs, which simply means objects beyond Neptune. And once that door opened, the outer solar system stopped looking empty. NASA says more than 5,000 of these distant objects have now been identified. Many are tiny, some are large, and a few are big enough to be called dwarf planets like Pluto and Eris. They live in and beyond the Kuiper Belt, a broad donut-shaped region that begins near Neptune at about 30 astronomical units from the Sun. 1 astronomical unit means the distance from Earth to the Sun, so 30 astronomical units means 30 times farther out than we are. The main part of the Kuiper Belt stretches to about 50 astronomical units, but the story does not stop there. Beyond it lies the scattered disk, a wider and stranger region that reaches outward to nearly 1,000 astronomical units. Some objects travel on huge paths that take them unbelievably far from the Sun, almost like they are trying to leave the family but never fully escape. That means the territory beyond Pluto is not a line at all, but a vast frozen wilderness. Scientists care about that wilderness for one big reason. These distant bodies are leftovers from the birth of the solar system, frozen pieces that never became full planets. They formed more than 4.5 billion years ago, then stayed in deep cold, far from the heat that changed worlds closer to the Sun. So if you want to know what the solar system was made of in its earliest days, this is where you look. But looking there has always been brutally hard. These objects are small, dark, far away, and colder than almost anything we can imagine in daily life. NASA says many of them are below minus 280 degrees Fahrenheit, which is about minus 170 degrees Celsius. That is so cold that gases we know on Earth can freeze like rock on their surfaces. For years, experts had a basic expectation. Because these worlds formed in the cold outer disk, they should be covered by simple frozen materials like water ice, carbon dioxide ice, methane ice, and nitrogen ice. Sunlight and radiation would slowly change some of that material, making more complex carbon-rich compounds on top. So the broad idea was clear, but the details stayed blurry. That blur was the problem. Older telescopes could tell astronomers some things like color and rough brightness, but not enough to read the fine chemistry of many ordinary TNOs. A few big or bright objects gave hints, yet most of the smaller worlds remained almost anonymous. Scientists were looking at a crowd of distant faces without being able to see the features clearly. Then the James Webb Space Telescope arrived with the exact kind of vision this problem needed. Its near-infrared spectrograph, called NIR-SPEC, can split faint light into a spectrum, which works like a chemical fingerprint. Webb reads light from about 1 to 5 microns, a part of the infrared range where many important ices and organic materials leave clear marks. For these distant icy bodies, that is like switching from a flashlight to a full lab scanner. One of the key observing efforts was a Cycle 1 program called DISCO TNOs, led by Nomi Penila Alonso. That program alone targeted nearly 60 trans-Neptunian objects and centaurs using about 98 hours of Webb time. And in Webb's first 2 years of science operations, NASA says the telescope gathered high-quality spectra for more than 75 TNOs. That is not a tiny step forward. It is a whole new level of access. What scientists expected was a messy collection of frozen leftovers with some differences here and there. What Webb actually found was something much sharper and much stranger. The data showed that many of these distant objects fall into 3 clear surface classes, 3 repeating chemical families, and that result was unexpected. The edge of the solar system was not random chaos. It was organized. Did you expect worlds beyond Pluto to sort themselves into hidden chemical families? If that reveal catches you off guard, tap like and leave a comment with the one fact that surprised you most so far. And if you want more real space mysteries built from actual data, subscribe. Now comes the part people remember. Webb did not just say these worlds are different. It showed a pattern strong enough to divide them into 3 groups. Scientists gave those groups simple nicknames based on the shape of their spectra in one important part of the infrared range. They called them bowls, double dips, and cliffs. Bowl-type objects show spectra shaped mainly by water ice. They also show some carbon dioxide ice and signs of silicate-rich dust, which is rocky material mixed into the frozen surface. The name bowl comes from the way the spectrum curves in that key region, like a broad dip rather than a sharp set of bites. These objects are the least red of the 3 groups. Double dip objects are where things get more dramatic. Their spectra show complex organic molecules, carbon dioxide and carbon monoxide ices together in a very unusual pattern. The key feature is a strong carbon dioxide signal with two peaks around it, making the line look like it sinks, rises, and sinks again. That shape was so distinct that NASA noted it had never been seen outside a laboratory in this exact way before. And then there are the cliffs. These are the reddest objects, and they appear to hold even more complex organic material and carbon dioxide than the double dips. They also show signs of methanol, which is a simple alcohol molecule that can exist as ice in these brutal outer conditions. Their spectrum drops in a way that looks steep and sudden, which is why the name cliff fits. And that might sound like a naming game, but it is much more than that. A spectrum is not just a color chart. It is one of the best ways scientists can tell what a distant object is made of. When Webb found these repeated shapes across many separate targets, it meant the chemistry was not random noise. It meant the outer solar system still carries structure from its earliest age. Here is why that shocked researchers. Before Webb, many people thought space weathering, impacts, and long years of radiation would blur these surfaces into a more confused picture. Yes, objects would differ, but maybe in gradual ways, not in three strong classes that keep showing up again and again. Instead, Webb found order where many expected a smear. It was like opening an old box of mixed photos and realizing they sort themselves into three lost families. There was another clue hiding in plain sight. The three groups also differ in visible color, especially at shorter wavelengths of light. Bowls are the least red, double dips sit in the middle, and cliffs are the reddest of all. That matters because color had been one of the few hints astronomers had before Webb, and now color finally connects to real chemistry. And then came one of the strongest signs that this was not an accident. NASA says every object in the undisturbed cold classical group belongs to the cliff class. Cold classical does not mean colder in temperature here. It means their orbits stayed relatively calm, round, and only slightly tilted for billions of years. These are thought to be some of the most untouched bodies in the outer solar system. That single pattern changes the story in a huge way. Scientists had expected the cold classical objects to be important because they likely stayed near their birthplaces. But now Webb says they are not just old and quiet. They share a common surface type, as if they formed under similar outer conditions and kept that memory. The clean match between orbit class and chemistry makes the ancient solar system feel real, not guessed. Did you ever think an orbit and a surface color could hold the same memory from billions of years ago? If that connection blows your mind, drop a comment with the word memory and subscribe if you want to keep following this trail. Because from here, the mystery stops being about Pluto and starts being about the whole solar system. To understand why, we need to go back to the early giant planets. Computer models say Uranus and Neptune did not always orbit where they are now. Long ago, they likely moved outward through a thick disk of icy bodies left from planet formation. As they shifted, their gravity scattered some objects away, trapped some in resonances, and left others in calmer zones. For years, astronomers used those orbits like footprints in sand. If an object had a certain path, maybe that said something about how Neptune pushed it around. That approach worked up to a point, but it left a big gap. An orbit can tell you where an object went, but not always where it was born. Webb starts filling that gap. If surface chemistry changes with formation distance, then the outer solar system suddenly becomes mappable in a new way. Now, scientists can compare both orbit and composition and ask a deeper question. Not just where is this object now, but where did it first come together? This is the leading idea NASA described. Bowl objects may have formed closer to the sun, where temperatures were higher and some compounds were less stable. In simple terms, those worlds may have been warm enough, in outer solar system language, to lose more of their carbon dioxide and methane from the surface. That would leave water, ice, and dust standing out more clearly. Double dips and cliffs appear to tell a different story. They may have formed farther out, in colder zones where carbon dioxide and methane could survive better. That would help explain why these classes keep stronger signs of those materials, along with more complex organics. In other words, the farther dark may have preserved chemicals that inner parts of the outer disk could not keep. And if that idea is right, then this is the incredible thing Webb revealed beyond Pluto. These worlds are not just frozen leftovers drifting without meaning. They may be a chemical map of the early solar system, a record of temperature zones from the time the planets were still taking shape. The edge of our system has been storing its own birth certificate, and that matters far beyond a naming chart in a paper. The materials on these surfaces connect to bigger questions in astrochemistry, cosmochemistry, and even astrobiology. Those are fields that study how matter changes in space, how planets form, and how ingredients linked to life get moved around. When you learn where water-rich and carbon-rich bodies formed, you learn something about the supplies available to young worlds. A close-up example helps make this feel less abstract. On January 1st, 2019, NASA's New Horizons spacecraft flew past Arrokoth, a small Kuiper Belt object discovered in 2014. And it looked like a flattened red snowman, a contact binary made of two lobes stuck together, and NASA called it the most distant and most primitive object ever explored by a spacecraft. Arrokoth gave us one frozen relic up close. Webb is now giving us the family tree around it. Pluto itself also looks different when you place it back into this wider crowd. It is about 1,477 miles wide, only around half the width of the United States, and it orbits in a region full of related icy worlds. Eris is similar in size, and many other TNOs are much smaller, often less than about 500 miles across. Webb is important because it can study those more typical objects, not just the famous giants. Did you grow up thinking Pluto marked the end of everything we knew out there? If so, hit like and tell me whether Pluto now feels lonelier or more important to you. And if you want the next Webb surprise the moment it lands, subscribe and stay close. Now, the tone of this story changes because this is not only about what happened, this is also about what is happening right now. NASA says Webb continues to observe trans-Neptunian objects every year, which means this picture is still being built, one target at a time. The mystery is active, not closed. Cycle 3 observations push that story farther. NASA says Webb is set to study a handful of TNOs and their satellites, and it will also take the first spectral observations of so-called extreme TNOs. These are objects on very stretched orbits that carry them far outward, in some cases well into the realm people loosely compare with interstellar space. No one knows yet how many more surprises those bodies hold. That matters because extreme objects could test the new idea hard. If their chemistry matches what scientists expect from their distance and orbital history, the new map gets stronger. If it does not, then something else may be shaping these bodies, maybe collisions, hidden heating, or a more complicated migration story. Either way, Webb does not end the debate, it upgrades it. And there is another live question in the data. Some future Webb programs focus on binary TNO systems, pairs of objects that orbit a shared center, and on objects with satellites. Scientists want to know whether those companions formed in giant impacts like a violent smash, or by growing together from the same cloud of material. That is not a tiny side issue. It changes how we think these outer worlds were assembled. The older picture often leaned on broad categories and rough guesses. A moon here might come from a collision. A pair there might be primordial, meaning very ancient and nearly unchanged since formation. But better spectra and imaging can start separating cases instead of lumping them together. And that is how real progress often looks in science. Not one answer, but sharper ways to tell answers apart. So right now, at this moment, Webb is not simply staring into deep space for dramatic pictures. It is running a slow investigation at the far edge of our own home system. Every new spectrum adds one more witness statement from a frozen object that has been waiting billions of years to speak. That is why this story feels unfinished in the best possible way. And here is the part that reaches back to us. The proposal behind DISCO-TNOs said these studies matter to our understanding of the origin of water and life on Earth and possibly elsewhere. That does not mean life is hiding beyond Pluto. It means the outer solar system may preserve clues about the raw ingredients and movement of material in the young solar system. Think about how huge that idea is. Earth did not form in total isolation, and the early solar system was a rough place full of moving debris, impacts, and exchanges of material. If icy bodies carried water-rich and carbon-rich compounds across great distances, then learning where those bodies formed tells us something about our own beginning. The frozen dark beyond Pluto may still be linked to the oceans and chemistry of Earth. Did you expect a story beyond Pluto to circle back to the question of how worlds like ours got their ingredients? If that connection grabs you, leave a comment with the word origin, tap like, and subscribe for more real science told simply. Because the next discovery out there may also change how we see ourselves here. There's also something deeply human in this. For centuries, the outer solar system was mostly blank space in our minds, a place of names without faces and distances without stories. Now, a telescope a million miles from Earth is reading chemical patterns from bodies so far away that sunlight takes hours just to reach Pluto. That is not normal progress. That is a leap in what our species can do. At Pluto's average distance, sunlight takes about 5.5 hours to travel from the sun, and Pluto is only one part of the wider trans-Neptunian region. Some detached bodies like Sedna come no closer than about 76 astronomical units and travel outward to around 1,200 astronomical units at their farthest points. When you say beyond Pluto, you are talking about a scale so big it almost defeats common sense. Yet Webb is pulling order out of that scale. What once looked like a loose swarm of red dots is becoming a structured population with shared histories. The words bowl, double dip, and cliff may sound simple, almost playful, but behind them is a serious result. The surfaces of these worlds are telling us they were born in different places and shaped under different conditions. That is the true twist in this story. People expected distance to hide the answer. Instead, distance protected it. Because these bodies stayed so cold and so far away, many of them may still preserve the chemistry of the early outer disk better than larger, more active worlds ever could. And that means the solar system remembers. Not in a poetic way only, but in a physical way, written into ice, carbon compounds, dust, color, and orbital families. Webb did not just reveal that there is something incredible beyond Pluto. It revealed that the frontier is organized, ancient, and still readable. Of course, the mystery is not over. What if more than 3 classes appear as the sample grows larger? What if some extreme TNOs break the pattern, or some satellite systems tell a different origin story entirely? Good science does not fear that kind of twist. It waits for it, tests it, and learns from it. So when you hear that NASA confirmed James Webb revealed something incredible beyond Pluto, this is what that really means. It means the edge of our solar system is no longer a silent pile of frozen leftovers. It is a coded archive from the era when planets were forming, and for the first time, we are starting to read whole sections of it. That is not the end of the mystery. That is the opening of a much larger one. What do you think Webb will uncover next out there beyond Pluto? A new chemical class, a stranger surface, or a clue about how our solar system was built? Subscribe, turn on notifications, and share this with someone who still thinks Pluto is just one lonely ice world. And leave your answer in the comments, because I really want to know which possibility feels biggest to you. Thank you so much for watching, and I hope to see you in the next one.